We started in an earlier chapter to look at probability distributions. May I remind you that the probability distribution is a mathematical function or a rule that gives the probability of occurrence of different possible outcomes of an experiment. We started to use the term statistical variable, which is a variable having values that occurs as a result of running the experiment. The probabilities of the outcomes of the experiment occurring represent the values of the statistical variable. We mainly work with two types of statistical variables, discrete and continuous. Discrete statistical variables are the ones that have values that can have gaps between them. For example, you count the number of books you have. They can be 0, 1, 2, and so on. You can't have 1.5 books. Continuous variables are the ones that show a continuous growth. Like, for example, if you want to measure your height. Even we estimate the height to the nearest centimeter, you'll say that your height is 164 centimeters, for example. You don't jump directly from 164 to 165. You take all possible values in between. That makes the statistical variable representing your height to be a continuous one. We looked in an earlier chapter at a certain type of experiment which is repeated n times with a constant probability of success, p, and where outcomes are independent from each other. That was discrete, and we counted the probability of having a certain number of successes within n trials, and we call that a binomial distribution. We looked then at another discrete model, which we called the geometrical distribution, where we counted under the same conditions as for binomial, we counted something different. We counted the probability that the first success will be within the X trial, on the X trial. These were the two discrete probability distributions that we studied. Today we are going to look at a continuous distribution, which is the most commonly occurring distribution in real life, in the life around us, and it's the normal distribution. As this distribution is very important, it was spending a bit of time to understand how it is formed. Imagine you go to the seaside and you collect data about the length of the shells. So that's what we are going to do. Whenever you find a shell, you record the numbers of the length of the shell. Of course, you would round probably to the nearest centimeter or millimeter in that case. But we know that this data is continuous because shells grow continuously. However, when we represent, we can think of representing through a histogram. If you look at the shape of this histogram while you continue measuring more and more shells, has a shape that resembles a bell curve. You'd always find in the middle the majority of the shells with some outliers, some very, very small or very, very large. That's a shape that is very often found in nature. That's why it's called the normal shape. I have all the data now from my previous measurement. I put the data in a table. As you might see, actually, that's not the data from my previous page, but I had already this Excel spreadsheet set up and it would take too much time to change it. So imagine these are the length of the shells. So I will call X the variable representing the length of the shells. And on the y-axis, I'm going to have probability of X being small x. So for example, probability of X being 100 here, it's around 0.0037, for example. I want to arrange them in a histogram. If my histogram will have a single bar, the minimum value in my table is 100, the maximum is 400. Look what happened with the area of the bar. The area is 300 times 0.0037 seems to be a bit less than 7. This will be 1.11. Since this one is less than 7, as we can see, it will be about 1. I will need to zoom in. So this area is 1. And it makes sense because the sum of all probabilities needs to be 1. So let's see what happens if I arrange all the data into 2 intervals. So I'll drag the slider for n and create 2 intervals. The length of each interval will be 150. The length of each interval will be 150. They are pretty close to each other. Now if I create 3 intervals, each with the length 100, see how a lot of data is in the middle. And I increase the number of intervals. Imagine that you regroup the data and you split the data, you arrange it into intervals that are more and more narrow. See how a lot of data is in the middle, and when you go towards the end of your distribution, you have less and less data. That's if I split into 100 intervals. So, for example, probability of x being between 250 and 250 plus something small here, the length of the interval, yeah, it's the bar of the height of the bar. Now I try, by changing these to sliders, to put on the top a shape that can help me estimate the distribution. And this shape is the shape of the normal distribution, the bell curve. In real life, we will not find distributions or data that follows exactly, 100% follows exactly the shape of the normal distribution. But many of the distributions in real life can be estimated as being normal. Also, you need to think that if I continue and instead of 100 intervals, I will have 1,000 or 1 million, the bars will be smaller and smaller, narrower, and the shape will be closer and closer to the normal distribution. The big idea here is that knowing the normal distribution will help me find probabilities. Probabilities are the area of those bars, as we know from a previous unit. So when I move on to normal distribution, it will be the area of the region that are under the normal distribution curve. Same as below, when the area of the small bars added up to 1, because it's the sum of the probabilities, same, the area below the distribution, the normal distribution, needs to be 1. So all this area is 1. Very often you'll not find distributions that are infinitely large to left and right, or can take values that are infinitely small or infinitely large. In my case, as we said, the lowest number is 100 and the highest is 400. However, we always think as the normal distribution as having values of x being possibly infinitely small or infinitely big. But these very, very big or very, very small values will occur very, very rarely, almost never. So that's why the tail of the distribution tends to be 0, because those probabilities will be 0 at one point. One other thing that is worth observing is what role has this mu. Mu is a mean of the distribution. See how it changes when mu becomes bigger or smaller, the position of the distribution changing. Sigma is the standard deviation. So you can have a bigger standard deviation or a smaller standard deviation. For smaller standard deviations, more data is around the mean. The distribution is not the spread. So that will be a standard distribution with a small standard deviation. For a large standard deviation, C85, the data is spread. So the curve will be more flat. Always the area under the graph is 1. This distribution does not match very well my data here. I'm just showing you that is more flat because the data is more spread. You'll have more data far from the mean. Whereas in the case when your standard deviation is small, more data is around the mean, therefore the probability of having a value around the mean is higher, or a set of values around the mean is higher. Having a function there and the coordinate system, this function must have a rule. And we have a rule for f of x, which is very, very complicated. We see a sigma, which is the standard deviation of the distribution, pi, the number pi from the area of a circle, mu, the mean of the standard distribution, and x, which is a value on the x-axis. We do not need to learn this formula. It's not that it's not part of our syllabus, but we never use it. We have other means to use the normal distribution. So remember, the normal distribution, the shape is used to calculate easily probabilities on the normal distribution curve, or under the normal distribution curve. What we know by now about this distribution is that the area under the curve is 1. So all this area is 1. We know that the shape is symmetric, even though in real life we'll not always find it symmetric. We know that it's symmetric by the mean. In this case, my mean is 258, so if I draw a line of symmetry here, it will go directly through 258. So mean is 258. Therefore, I know that probability of x being bigger than the mean will be for sure 0.5 or 50%, because this area is half of the area because of symmetry. So it will be 50%. I also know for sure that probability of x smaller than mu will be also 0.5, also 50% is area to the left. Another thing I just learned is that x can have infinite values, though it will never happen in reality because this tail is basically 0. The probability on this tail is basically 0. I need a notation, same as I had a notation for binomial distribution. The notation for normal distribution is x is normally distributed. My variable is called x, remember? So x is normally distributed, and there are two parameters, mu, mean, and variance. Sigma is a notation for the standard deviation, always. And sigma square will be the variance. The official notation for the normal, and that's how we need to learn it, is that in this position is always a variance. So let us remember that. For now, there are just these probabilities that I can find on the normal distribution, but over time we learn how to find other probabilities. A big question that students always have, and it's a very good question, is it probability of x bigger than mu, or probability of x bigger or equal than mu? Whereas for discrete distribution, that was a big difference, because it would mean if you include or not mu. In the case of the continuous distribution, it makes no difference, because for a continuous distribution, probability of x being exactly the value mu is 0. And I'm going to explain you why. Imagine x measures your height. You grow continuously. If I want to find what's the probability of you being exactly 170 centimeters, then there is just one success value, 170, over probability of all outcomes. You have infinitely many numbers that can represent your height because it's continuous. So you'll have 1 over something very, very big, which is infinity for a probability, so the probability will be 0. That's why in the case of a normal distribution, it doesn't matter if we put bigger, bigger or equal, smaller, smaller or equal, because probability in each point is 0. Later on, as mentioned, we will use this distribution to calculate probabilities, like for example, probability of x being between a and b. And again, it doesn't matter if it's less equal, less equal, it doesn't matter. And this will be represented if you take a here, wherever it will be, and b somewhere here, I don't know, depends on the numbers. Probability of x being between a and b will be this area under the graph. And I know in the pure maths you do calculus and you use integrals. Here I'm not going to use integrals, and we're going to use table of values to find the probabilities, but that's our aim, to use this shape and find probabilities. Before going into exploring the normal distribution, let us ask ourselves one question. There are many phenomena in real life that follow normal distributions. Like, for example, the height of woman. You have very many in the middle, and once you go to high heights or low ones, you have less and less women. How about the weight of people? You have a lot of them in the middle, and once you go towards the very high numbers for weights and very low, you have less people. So these two variables follow both the normal distributions. So the big question is, I know, for example, that Taylor Swift is very tall. And I know, for example, that Oprah is, well, a bit chubby. How can I compare them? Which one is more rare? If I think of the height of women around the globe, and I think of the weights of women around the globe, which one is more special? Taylor Swift or Oprah? So there is a need of comparing different distributions. That's why we are going to refer both of them to, or going to move both of them on a single distribution, kind of unifying them so that we have a term of comparing them. And this will be the standard normal distribution. The standard normal distribution has a special letter because it's a special distribution, and we call it Z, standard normal distribution, and is normally distributed with mean 0 and standard deviation 1, variance 1 squared, which is also 1. I like to write 1 squared so that I make it clear which one is standard deviation, which one is variance. So this Z is called the standard normal distribution. If I am able, on the standard normal distribution, which has a shape similar to that, to say, oh, this is a distribution of how tall people are, and I don't know, let's assume the mean, it's what can be the mean around the globe, I don't know, 160 centimeters. And this is a distribution of weights, and what can be the mean weight, I don't know, 60 kilograms, maybe. If Taylor Swift, for example, is on this distribution here, and Oprah is on this distribution here, see, they are very different. I can't compare one with other. But if I can bring them both on this distribution, and I say, okay, one is here, then I have less people which are more awkward, let's say, than the person here, than the person here. So then I can compare them. So that's a big idea. Now the question is, how do I move from any distribution, normal distributing with mu, mean, and sigma squared, the standard deviation, how do I move to the Z distribution? The idea we are going to explore now is how we move from any non-standard normal distribution to a standard normal distribution. A standard normal distribution has a mean 0 and the standard deviation 1. A non-standard can have whatever mean I want and whatever standard deviation I want. So let's take the mean 65, for example. And let's take the standard deviation 5. It can be smaller, meaning that more data is toward the middle, or it can be larger. Let me take a standard deviation of 3, for example. How do I know how points from here are mapped on the standard normal distribution? What joins the two graphs together is that the area under the graph is 1. They are not drawn to scale, so maybe they don't look the same, but the area under a normal distribution is always 1. Therefore, if your x on the non-standard normal distribution is 65, for example, the mean, area to the left is 0.5. And the corresponding Z score for this 65 is 0, because the area to this left is also 0. It makes sense, for example, if I take here an area to the left as being 18%, area to the left, the corresponding value on the Z distribution or standard normal distribution to have the same area to the left, 0. Therefore, I'd say that 62.22 corresponds to 0.927. And if I keep moving this, I will say 63.04 corresponds to minus 0.654, and so on. So that's how the two distributions are related. Therefore, I want to find the formula between this x and the z-score here. That's called the z-score. The formula is the following. It's in your formula booklet. Z equals x, the point on the non-standard normal distribution, minus mu, the mean of the standard distribution, over sigma. So for this x, the z-score will be the x itself minus mean, 65, over standard deviation 3. So the z-score will be 0.844, which is here. This is how I move between the two distributions. Conversely, if I know z from this equation, I can find x, so I can move from z distribution to the non-standard and back using this formula. Notations to reflect this situation are, we need to get our notations right as well. X is normally distributed with 65 is the mean, always first coming, and 3 squared is the variance. So mean is 65 and mu, I use it for the mean. Sigma is standard deviation is 3. Variance of x is 3 squared or 9. What do I see on this diagram is that probability of x smaller than 67.53 is area, this area here, which is 80%. On this distribution, probability of z smaller than 0.844, right, from here, is also 80%. These two are related, these 2 points are related by the formula z equals x minus mu over sigma. So whenever I know this point, I can find z. Whenever I know z, I can go back to that distribution. This will allow me, in the case I have many distributions and I have some points, to bring them to the z distribution. Find the z-score. We say that for x equals 67.53, the z-score is 0.844. And then we can compare the z-scores, and therefore the standard normal distribution help me bring and compare different distributions. Let's discuss this example from your textbook. You can pause the movie and read the question, please. I think that the authors of the textbook could have done better, because if we think that x is the scores in a test, and it seems from the question that the scores are number of marks, you cannot award half marks, you need to award the full number of marks. Therefore, x is not a continuous variable, it's a discrete one. Whereas they will ask us to find z-scores, which are characteristic to continuous distributions and only to normal distributions. But we're going to omit this. Let's assume the tests are continuous, which are not. Another mistake in this question is that actually they do not say that the scores in the test follow a normal distribution. And not always a test in the scores in a test follow a normal distribution. Imagine I have a class where I have some very weak kids and they will not do very well in the test, and then I have some very strong kids which will do very well in the test. So that's a distribution. And I can't use the techniques of standardizing because that's not a normal distribution. I actually had about 15 years ago such a class. It was very difficult to work with them. All their test scores look like that if I created a distribution. So I will make here, to solve this question, 2 assumptions that the author should have made. First, that the scores are continuous, and then that they follow a normal distribution. If we assume that, you can find for history the z-score. I remind you, z equals x minus mu over sigma. So for history, z is 75 minus mu over sigma. And for math, that's the z-score. If we think of the two on the standard normal distribution, the history, which is 1.5, is here, and the math is 1.2, which is here. Therefore, Alexandra's standardized score Z is higher in history, so she has done better in history compared to her mates. Now, this is a better question because they talk about x being the height of plants, which is continuous, but they don't tell us as well that it's a normal distribution. The question should state. So what do I see here in this example is the following. Let's read it. The mean height of a center plant A is 67. And the heights have a standard deviation of 5. So 67 and the standard deviation of 5. Another plant B has a mean height of 63. I'll put another scale, I'll put 63 here so that we see that it's actually the aim is to see that you have on the right here 50%, same as here. The same proportion of both types of plants is taller than 77 centimeter. So if I would have 77 here and 77 here, the percentage here is the same as the percentage here. Now that's an interesting question because actually I know both scores on both diagrams, but I don't know in one of the cases sigma. So X is normally distributed with 67 and I'm given the standard deviation here, which is 5, so 5 squared. And X here, or let me call it Y, is normally distributed with 63 and sigma squared. I do not know sigma. So how am I going to relate the two? Through the standardized normal distribution. So I know that if I map both of them on Z, the area to the left, to the right will be the same. So let's map them both. If I map 77 here, this point, let me call it Z, will be Z equals X minus mu over sigma. But now I know that if I map this point here, will be at the same point. So it will be the same as 77 minus mu over sigma. And here I have an equation. I do not know sigma, so from the equation 77 minus 67 over 5 equals 77 minus 63 over sigma, I can find sigma. And of course, I can use my calculator to find sigma.